Have you ever looked up, past Mars, past the asteroid belt, and just felt drawn to those huge swirling planets way out there? I mean, Jupiter, obviously.
Yeah.
The biggest one, the king of the solar system. It just looks so powerful and mysterious. What is it about these gas giants that grabs our attention?
It's definitely more than just how big they are, isn't it? There's something inherently fascinating about things so vast, so alien compared to Earth. And Jupiter, well, humans have been watching it for thousands of years. Always curious, always trying to figure it out. Its place in the sky, what it is, and, even if there could be life somewhere in its system, it's not just a ball of gas. It's tied up in our history, our myths, our science.
Right, it's got layers. And that's exactly why we wanted to do a deep dive today. We're going to
Oh.
trace Jupiter's story through human history, from like the very first people looking up just with their eyes all the way to these incredible robot explorers we send now.
And yeah, absolutely, the search for life. That's always the big question, isn't it? It is. And the sources we've pulled together for this are, well, pretty diverse. We've got ancient Babylonian clay tablets, Roman myths, the latest NASA data from probes like Juno, even some really out there theoretical physics. It paints a really rich picture, Jupiter as this mirror reflecting our own understanding of the universe changing over time.
So our mission today is to pull out the key stuff for you, the really important bits of knowledge, maybe some surprising facts you haven't heard, those aha moments. So by the end, you feel like you really get Jupiter a bit better. All right, let's jump in. We're heading for the king of the planets.
Okay.
Okay, let's start way back. Before telescopes, before any fancy equipment, just looking up. Jupiter, along with Mercury, Venus, Mars, and Saturn, they've always been there, right?
That's
Visible
true.
for thousands of years. So it's not like one person discovered it. They were these bright lights that moved differently from the stars. They didn't twinkle the same way.
Exactly. They were the wanderers. And what's truly amazing when you think about having no instruments is what ancient cultures figured out. Take the Babylonians. We've found these incredible cuneiform tablets, and they show the Babylonians were using an astronomical technique that was, and this is staggering, maybe 1,500 years ahead of its time.
Wow, 1,500 years. That's hard to even wrap your head around for that period. What were they doing? Tracking Jupiter?
They were tracking Jupiter's path across the sky, yeah. Now, from here on Earth, Jupiter doesn't seem to move smoothly. It looks like it speeds up, slows down, even goes backwards sometimes, that retrograde motion we talk about. It's all because both Earth and Jupiter are orbiting the sun. Must have been baffling. But the Babylonians, somehow, they worked out a mathematical system to predict its position, accounting for that changing speed.
Okay, so they weren't just watching, they were calculating this complex dance. What does that tell us about their maths, their view of the cosmos?
Well, it shows they had this abstract grasp of how speed and position relate to time. We usually think of that kind of thinking, analyzing motion over time, graphically or abstractly, starting much later. Like Oxford and Paris around 1350, or Isaac Newton with calculus. But the Babylonians were doing something conceptually similar way earlier. Their calculations on these tablets match up perfectly with a geometric method. They figured out the distance Jupiter traveled, say, 10 degrees, 45 minutes over 60 days by calculating the area of a trapezoid on a graph plotting speed against time.
Whoa, hang on. So they were using geometry, drawing shapes, to represent speed and distance. That is like a precursor to calculus.
It really is. And they even took it a step further. They figured out how to divide that trapezoid into two smaller ones of equal area to find the exact time it took Jupiter to cover half the distance. It's just a level of mathematical thinking about the physical world that's kind of revolutionary for that era. It shows this abstract ability we didn't think existed back then.
That is genuinely mind-blowing.
It
It
is.
makes you rethink the whole timeline of scientific thought and the idea that this knowledge was just lost.
Exactly. It really challenges the idea that science just progressed in a straight line, mainly through Europe. Brilliant ideas can pop up anywhere, anytime, and then just vanish if the culture changes or the way knowledge is recorded disappears. Like when Babylonian culture and the cuneiform script faded out around 100 CE. This incredible technique was seemingly forgotten, only to be reinvented centuries later.
A lost piece of intellectual history. It's incredible. But some of their astronomical knowledge did survive, didn't it? It wasn't a total wipeout.
No, thankfully not. Other important Babylonian ideas did get passed on, translated into Greek, and influenced later astronomy. We still use things derived from them today. The signs of the zodiac, for example, that comes from their mapping of the constellations along the sun's path. And crucially, the way we divide circles into 360 degrees, and degrees into 60 minutes, and minutes into 60 seconds. That base 60 system, that's a direct legacy from the Babylonians. We use it every single day. way.
Yeah.
Amazing. Okay, so from Babylonian maths, let's leap forward centuries to the invention that changed everything, the telescope. And the name everyone associates with turning it skyward first is Galileo Galilei.
Right. Galileo gets the primary credit, and deservedly so, for being the first to really systematically use the telescope for astronomy and publish his findings. Looking at Jupiter was one of the first things he did. And seeing those 4 tiny stars circling it, what we now call the Galilean Moons, that was huge. It showed not everything orbited the Earth, which was a massive boost for the sun-centered model of Copernicus. We'll definitely talk more about those moons later.
Yeah, they're crucial. But wasn't he the only one with a telescope pointed up back then? Or were others doing similar things?
He wasn't entirely alone, no. It was a time of rapid innovation. Thomas Harriot in England and Simon Marius in Germany were also using early telescopes for stargazing around the same time, even observing Jupiter's moons independently. Galileo was just incredibly thorough in documenting everything, drawing what he saw, and really pushing his conclusions out there, which is why he's so central to the story. But the telescope itself sparked a wave of new observation across Europe.
It's fascinating how technology drives discovery like that. Okay, we've looked at the science starting to emerge. But what about the older stories, the mythology? Jupiter, the planet, is named after the Roman king of the gods. That's no accident.
Absolutely not. And the name itself tells you a lot. Jupiter likely comes from old Proto-Italic words, Jus for day or sky, and Patur for father. So literally sky father. It perfectly captures his role.
The big boss in the sky, king of the gods.
He really was. Jupiter, or Jove, was the top god in the Roman pantheon. God of the sky, god of thunder, the ultimate authority. He was also seen as the special protector of Rome and its empire. People prayed to him for victory in battle, for the well-being of the state. His worship was absolutely central.
And he had some pretty dramatic attributes, right? Lightning bolts, storms.
Oh, yeah. He was the one wielding the lightning, controlling the weather. And they believed he communicated with humans through auspices. These were divine signs, thunder, lightning strikes, even how birds flew. They saw these as messages, warnings, or signs of approval from Jupiter.
So he wasn't a distant god. He was actively involved, judging by these signs, and important for law and order, too.
Very much so. In the official state religion, he was the guardian of oaths, treaties, keeping good faith. Breaking an oath sworn by Jupiter was a huge deal. His cult wasn't just in Rome. It was widespread across Italy. Everyone recognized him as the supreme god.
Did he have, like, a main divine partner, a queen?
Yes, his primary partner was Juno, his sister and wife, who was the goddess of marriage and women, also a very powerful figure. There's also this interesting old myth from Praeneste depicting Fortuna, the goddess of luck, basically nursing Jupiter and Juno as babies, which suggests just how ancient and fundamental they were considered, even before the more familiar Roman myths took shape.
Huh, interesting. And I think you mentioned something about his name echoing in our week.
That's right. One of his titles was Jupiter Tonans Jupiter the Thunderer, and that connects directly to Thursday. Thursday is named after the Norse god Thor, or the Germanic gods Thunor or Donar, all thunder gods. Very similar to Jupiter in that aspect. So every Thursday, we're unknowingly referencing this ancient association between the planet, the god, and thunder.
That's a cool little connection. Okay, so we've seen Jupiter through ancient eyes, through myths. Let's shift back to the science, to peeling back its layers in the modern era. Rings, storms, what's going on inside. Let's start with the rings. For a long time, people thought only Saturn had rings.
Right. That was the standard thinking, absolutely. Before the late 1970s, Saturn seemed unique. Scientists even came up with models to explain why only Saturn would have rings. It was just accepted fact.
So what blew that idea out of the water? When did we realize Jupiter had them too?
That came thanks to Voyager 1. As it flew past Jupiter in March 1979, it snapped images that clearly showed a faint ring system. Uranus's rings had actually been found just 2 years earlier in 1977 from Earth-based observations. So Jupiter became the third known ringed planet. It completely changed. The picture rings weren't a Saturn-only phenomenon. Ground-based telescopes quickly confirmed Voyager's find.
Are Jupiter's rings like Saturn's? Big and icy?
Not really, no. They're much fainter, much thinner, probably only about 30 kilometers thick, maybe 9,000 kilometers wide in total. They seem to be made mostly of fine dust particles, likely kicked up by micrometeoroid impacts on Jupiter's small inner moons, like Amalthea and Thebe. It's thought that Amalthea's gravity helps act like a shepherd moon, keeping the main ring's outer edge sharp, so much more subtle than Saturn's magnificent icy rings.
Okay, so subtle rings. But there's nothing subtle about Jupiter's most famous feature, the Great Red Spot. That thing's a monster.
It really is the biggest storm in the entire solar system, hands down. It's a gigantic anticyclone, basically, a high-pressure system in Jupiter's southern hemisphere. And it's been churning away for at least 150 years that we've consistently observed it, maybe much, much longer. A truly persistent weather feature.
You say maybe longer. Are there hints it was seen even earlier than the late 1800s?
There are, yeah. Some sketches by Robert Hooke in 1664 or observations by Giovanni Cassini around 1665 might show it or something like it. The problem is we can't be totally sure if it was the same storm or if it perhaps faded and reformed. Consistent observations really only start from 1878, after C.W. Pritchett clearly identified it. Since then, it's been constantly watched.
And it's not static, is it? I hear it's changing, shrinking, changing color.
It is definitely dynamic. The spot has been noticeably shrinking for decades. It's smaller now than it's ever been reliably measured. And since around 2014, its color seems to have intensified, becoming a more deep, ruddy orange. Scientists are still debating why. Maybe changes in the atmospheric chemistry up high involving chemicals like ammonia reacting with sunlight, or perhaps changes in how gases are circulating within the storm, dredging up different materials. We don't fully know yet.
Does studying a monster storm like that, even on a gas giant, teach us anything about weather back here on Earth?
Absolutely. Even though Jupiter's atmosphere is wildly different, mostly hydrogen and helium, no solid surface. The fundamental physics of fluid dynamics, how energy moves around, how storms form and persist, that's universal. Studying the Great Red Spot gives us this incredible natural laboratory for understanding large-scale, long-lived atmospheric vortices and energy transport in ways we just can't replicate here. It helps refine the models we use for Earth's weather and climate, too.
And it's not the only big storm there, right? Didn't some smaller storms merge to make another red spot?
That's right. There's the feature often called Oval BA, or sometimes Red Spot Junior. It formed between 1998 and 2000 when three smaller white oval storms, which had been observed for decades, collided and merged. And interestingly, after merging, it also turned reddish, though not as intense as the Great Red Spot. It shows how dynamic Jupiter's atmosphere is, with storms constantly forming, merging, and evolving.
Wow. And I read something really weird about the temperature above the Great Red Spot. It's hotter up there.
Yeah, that's one of the big surprises from recent observations. The atmosphere hundreds of kilometers above the storm's cloud tops is significantly hotter than anywhere else on Jupiter at that altitude by hundreds of degrees. The leading theory is that the incredible turbulence within the storm generates powerful atmospheric waves, maybe acoustic waves like sound or gravity waves. These waves travel upwards and deposit their energy in the thin upper atmosphere, heating it dramatically. It just shows the colossal amount of energy churning away down below.
Okay, from the wild atmosphere down into the depths. Jupiter actually gives off more heat than it gets from the sun. That's weird. How does it generate its own heat?
It's a process called the Kelvin-Helmholtz mechanism. Essentially, Jupiter is still slowly cooling down from its formation billions of years ago.
Cooling down, but that makes it hotter inside. How does that work?
Right, it sounds backwards. But as the planet radiates heat out into space from its surface layers, it cools slightly. This cooling causes the internal pressure to drop just a tiny bit. Because Jupiter is so massive, its own gravity then causes the whole planet to contract, to shrink, very, very slowly. And when you compress a gas, which is mostly what Jupiter is, it heats up. So this incredibly slow gravitational shrinking converts gravitational potential energy into internal heat.
So it's basically shrinking itself warm. How much is it shrinking? Like, noticeably.
Oh, it's minuscule. The estimate is around 1 millimeter per year. Far too small to see directly. But over the age of the solar system, this tiny contraction adds up to a significant amount of energy released. The Cassini probe actually measured this internal heat escaping Jupiter during its flyby, about 7.5 watts per square meter. It confirmed this process is definitely happening.
And speaking of the inside, the Juno mission has given us some new ideas about Jupiter's core and also its lightning, right?
Juno has been revolutionary for understanding the deep interior. Its gravity measurements suggest Jupiter might not have a small, solid, well-defined core like we used to think. Instead, the core seems to be larger, more fuzzy or diluted, possibly mixed with the metallic hydrogen layer above it. It's forcing scientists to rethink how giant planets form and evolve. And yes, Juno's also found lightning, but it's different from Earth's.
How is Jovian lightning different? Ours comes from water clouds.
Exactly. Earth lightning mostly happens in clouds with liquid water droplets and ice crystals, but Juno detected lightning flashes high up in Jupiter's atmosphere, in regions likely too cold for liquid water. They call it shallow lightning. The thinking is it might be generated by processes involving ammonia water ice crystals, forming slushy mush balls that interact electrically. It's a whole different kind of storm
Wow.
electricity.
Ammonia mushball lightning.
We'll do
Okay.
it.
So Jupiter itself is endlessly complex, but it's not alone out there. It has this incredible system of moons. Let's dive into those, starting with the big four that Galileo saw.
Right, the Galilean Moons, Io, Europa, Ganymede, and Callisto. Discovered by Galileo in 1610, a huge moment. He initially called them the Medicean stars after his patrons, but also used Roman numerals, Jupiter the first, 333, starting from the closest. The mythological names we use now, suggested by Simon Marius actually, didn't really catch on widely until the mid-20th century. Before that, astronomers often just used the numbers.
And out of those four, Europa is the one that gets everyone excited about aliens, right? The potential for life. Why Europa?
Europa is incredibly compelling, yes. The main reason is the strong evidence that beneath its icy, incredibly smooth surface, there's a vast ocean of liquid saltwater. That smoothness itself is a clue. It suggests the surface is young and geologically active, constantly being resurfaced, likely by water or slush erupting from below and smoothing over craters. And where there's liquid water, there's the potential for life as we know it.
But it's so far from the sun, so cold out there. How can an ocean stay liquid?
That's the key, tidal heating. Europa is constantly being squeezed and stretched by Jupiter's immense gravity. Its orbit isn't perfectly circular, and it's also in resonance with Io and Ganymede, meaning they give it regular gravitational tugs. This constant flexing generates friction deep inside Europa, creating enough heat to maintain that subsurface ocean in a liquid state, despite the freezing temperatures at the surface. It's like kneading dough, it warms up.
And that heating might also drive geology, like plate tectonics on the ice. Could that help life?
Potentially, yes. That same tidal energy could drive activity in the ice shell, maybe something like plate tectonics, where slabs of ice shift and subduct. This could be really important for habitability because it provides a way to transport chemical compounds from the surface, perhaps delivered by impacts or radiation, down into the ocean. Also, there's evidence suggesting the ocean is likely in contact with a rocky mantle below. If there are hydrothermal vents on Europa's seafloor, like on Earth, they could provide chemical energy and nutrients, forming an ecosystem independent of sunlight.
Hydrothermal vents. That's exciting. And haven't we actually seen hints of that water escaping, like geysers?
Yes, that's one of the most thrilling developments. The Hubble Space Telescope has detected faint evidence of plumes of water vapor erupting from Europa's surface, possibly hundreds of kilometers high. And a reanalysis of old data from the Galileo probe also seemed to show it flew through a plume back in the 90s without realizing it at the time. These cryogeysers, if confirmed and regular, are incredibly exciting because they mean we could potentially fly a spacecraft through them and sample the ocean's composition directly without needing to drill through miles of ice.
Wow, just fly through and sniff for life signs. That would be amazing. What about the surface itself, these weird chaos terrains?
Ah, yes, the chaos terrain. These are areas where the icy surface looks completely disrupted, jumbled, like huge blocks of crust have broken apart, shifted, and refrozen in a chaotic matrix. One idea is that these are places where plumes of warmer ice, or perhaps even pockets of water closer to the surface, have melted or disrupted the overlying crust. Though the dominant model now favors a pretty thick ice shell overall, maybe 10 to 30 kilometers thick, over a much deeper ocean, perhaps 100 kilometers deep.
100 kilometers deep. That's vastly deeper than Earth's oceans. How much water are we talking about?
If those estimates are right, Europa's subsurface ocean could contain 2 to 3 times the total volume of all of Earth's oceans combined. It's just an immense amount of liquid water locked away beneath that icy crust. Truly one of the great potential habitats in the solar system.
Is our picture of Europa changing all the time? Any recent news that adds maybe complications?
Science is always refining the picture. For example, a study reported in March 2024 suggested that the amount of oxygen being produced on Europa's surface by radiation hitting the ice might be significantly less than some earlier estimates. Oxygen could potentially dissolve into the ocean and support complex life, so lower production makes that scenario maybe less likely, or requires different chemistries. It doesn't kill the idea of life, but it adds nuance. Habitability is complicated.
Okay, does it have an atmosphere? Does it spin normally?
It has an atmosphere, but it's incredibly thin, tenuous, really. Mostly oxygen sputtered off the surface ice by radiation. Hubble saw it first, then Galileo confirmed it. And yes, it's tidally locked, like our moon, so it keeps the same face towards Jupiter. Although, interestingly, some studies of its surface features suggest the icy shell might have slipped relative to the interior in the past, meaning it wasn't always perfectly locked, or the whole shell can move independently, which again points to that liquid layer, the ocean, decoupling the crust from the core.
Europa sounds incredible. But it's got that neighbor, Io, which is the complete opposite, right? Total volcanic hellscape.
That's a good way to put it. Io is the most volcanically active body in the solar system, thanks again to even more intense tidal heating from Jupiter. Juno's recent findings are pretty spectacular. Using its microwave instrument to peer beneath the surface, combined with infrared images, it's basically mapped out vast regions of subsurface magma. They're seeing still, warm, molten rock practically everywhere they look, under the surface, suggesting a global magma ocean or at least extensive networks of magma.
A global magma ocean. And all that volcanic stuff spewing out actually affects Jupiter itself.
Massively. Io constantly blasts plumes of sulfur dioxide and other volcanic materials into space. This material gets ionized and trapped by Jupiter's magnetic field, forming a huge donut-shaped ring of plasma around Jupiter called the Io plasma torus. This torus is a major source of the charged particles that feed Jupiter's incredibly powerful radiation belts, making the whole environment near Io extremely hazardous. It's a very dynamic relationship.
Okay, and the last of the big four is Callisto. What's its story?
Callisto is the outermost Galilean moon, Jupiter the fifth. It's quite different from the others. Its surface is extremely old and heavily cratered, meaning it hasn't had much geological activity for billions of years, unlike Europa or Ganymede. It's kind of a fossil world in comparison. There's evidence suggesting Callisto might also have a subsurface ocean, but if it does, it's likely much deeper down and probably not interacting with a rocky core in the same way as Europa's, making it less compelling from a habitability standpoint, at least based on current thinking. We use terms like Callistoan or Callistonian when talking about it.
Okay, so from ancient math to maybe alien oceans, Jupiter and its family are just full of surprises. Which brings us to the human quest to explore it. The robot probes we've sent, the future plans, and the really big question, could humans ever go there?
Our robotic explorers have been absolutely essential. There are eyes and ears out there, and sending them isn't simple. Mission designers have choices. You can go for a fast, direct flyby like the Pioneers and Voyagers did, great for reconnaissance. Or you can take a longer looping path, maybe using gravity assist from planets like Galileo or Juno did. That takes more time, but lets you get into orbit for long-term study or saves fuel.
Let's quickly run through some of those key robot achievements. What did they tell us?
Okay, quick recap. Pioneer 10 and 11 in the early 70s were the first to brave the asteroid belt and get close-ups, measuring the magnetic field and radiation. Huge first step. Voyagers 1 and 2 in 79 gave us those iconic images, discovered the rings, saw Io's volcanoes erupting, got our first detailed look at the moons, game changers. Galileo orbited Jupiter from 95 to 03, dropped a probe into the atmosphere, gave us tons of data on Europa suggesting the ocean, invaluable. Juno, orbiting since 2016, is mapping Jupiter's gravity and magnetic fields like never before, giving us clues about that fuzzy core, seeing the weird lightning, mapping Io's magma, flew by Europa recently. Still going strong. And don't forget Hubble, observing from Earth orbit, crucial for spotting Europa's plumes and atmosphere. Even Cassini, on its way to Saturn, swung by Jupiter and measured its internal heat output accurately. Each mission builds on the last.
An amazing robotic legacy. So what's next?
Yeah.
Especially for Europa, given all that potential.
The big one on the horizon is NASA's Europa Clipper mission. It's specifically designed to investigate Europa's habitability. It's got funding, aiming for launch in the mid-2020s. It won't land, and it's not expected to find life directly, but it will do dozens of close flybys.
Flybys? Why not orbit Europa directly if it's so interesting? Is it the radiation again?
Exactly. Orbiting Europa would mean sitting inside some of the most intense radiation belts, which would fry the spacecraft's electronics relatively quickly. So Clipper will orbit Jupiter in a way that allows for these repeated, fast dips close to Europa, 45 of them planned. Someone described it as running into the fire, grabbing some valuables, and running out. Each pass gathers data high-res images, ice-penetrating radar to map the ocean, spectrometry to analyze the surface composition, then it swings back out to safety to process and transmit. It's a clever way to manage the risk while getting great science.
It makes sense.
Yeah.
Were there other cool ideas for exploring these moons that maybe didn't happen?
Oh, lots of ambitious concepts have been floated over the years. There was an ice clipper idea that would literally fire an impactor into Europa and have a spacecraft fly through the debris plume. There was the Jupiter Icy Moons Orbiter, or JIMO, a really ambitious concept using nuclear fission power, which would have allowed long-term operation in the Jupiter system, but it was canceled back in 2006 due to cost and complexity. A dedicated Europa orbiter was actually approved in 1999, but canceled in 2002. It would have carried that ice-penetrating radar. And yeah, people have dreamed up landers, even cryobots that could melt their way down through the ice shell to reach the ocean directly. That's still the ultimate goal for many.
So Europa is definitely a hotspot. But are there other places, maybe easier places, to look for life out there? Like Saturn's moons?
That's a really active debate in the astrobiology community. Saturn's moon Enceladus is another prime target. Cassini actually flew through plumes erupting from cracks near its south pole and confirmed they contain water, salts, silica dust, and complex organic molecules, basically, all the key ingredients for life as we know it, readily accessible. And the radiation environment at Saturn is much milder than Jupiter's. Some argue Enceladus is actually a better, or at least easier, target right now. Then you have Titan, Saturn's largest moon, which is completely different again. It has liquid methane lakes, a thick nitrogen atmosphere, complex organic chemistry. It forces us to think about life based on totally different solvents and metabolisms. Could life exist in liquid methane? Titan makes us ask that question.
Okay, robots are paving the way. But the ultimate dream for some is humans going there. Is human travel to Jupiter even remotely feasible?
Feasible is a strong word right now. It's monumentally difficult, far beyond anything we've ever attempted. Just the travel time is immense. A one-way trip using current or near-future propulsion would take close to 6 years. 6 years just to get there.
6 years in a spaceship. The supplies alone. Food must be a killer issue.
It's staggering. A rough estimate for a 4-person crew is needing something like 8,000 pounds or nearly 4,000 kilos of food per year. So for the 6-year outbound trip, you're talking nearly 50,000 pounds of food. And then you need food for whatever you do there and for the 6-year trip back, plus reserves, not to mention water, air, spare parts, scientific equipment. Everything has to be brought from Earth. The launch mass required would be astronomical.
And then looming over everything is the radiation we keep talking about.
That is the single biggest showstopper, honestly. It's not just challenging, it's potentially deadly. Those radiation belts around Jupiter, fed by the solar wind and especially by Io's volcanoes, are incredibly intense, much, much worse than Earth's Van Allen belts or anything encountered during the Apollo missions.
Can you put some numbers on it? How bad is it compared to, say, what astronauts experience now?
Okay, radiation doses measured in sieverts, SVIA. On the International Space Station, astronauts get maybe 0.3 SV over 6 months. NASA's career limit for astronauts is around 1 SV, depending on age and sex. Around Europa, the daily dose is estimated at several sieverts. You'd exceed your entire career limit in a matter of hours. Near Io, it's even worse, maybe 36 SV per day. A dose of 5 IA is considered likely lethal for humans. You'd reach that lethal dose near Io in less than 4 hours without massive shielding.
4 hours?
Yeah.
And that's a no-go zone. It's not just slightly more radiation, it's orders of magnitude more.
Exactly. Someone calculated it's like 5 orders of magnitude, 100,000 times more intense than background cosmic rays at sea level on Earth. Trying to visualize that difference. It's like comparing a whisper to a continuous rock concert inside a particle accelerator. It's just fundamentally different.
So is there like a safe distance, a keep-out zone?
It's not a sharp line because it depends on how long you stay and how much shielding you have. But for humans, without shielding technologies far beyond what we currently have, you'd really want to stay hundreds of thousands of kilometers away from the most intense inner belts around Io and Europa. Even then, the background radiation in the Jupiter system is high.
Is NASA working on ways to deal with this kind of extreme radiation for future deep space missions, even if Jupiter is the ultimate extreme?
Yes. NASA's Human Research Program, HRP, is constantly working on radiation mitigation. It's crucial for any long-duration mission, like going to Mars, let alone Jupiter. They research advanced shielding materials, potentially using water or specialized plastics. They're developing better radiation detectors and dosimeters so crews know their exposure in real time. They study the biological effects using particle accelerators on Earth to simulate space radiation. And they look at countermeasures like potential radioprotectant drugs, though those are still very experimental. But Jupiter's levels are so high, current strategies would need a massive leap forward.
Okay, so humans visiting Jupiter seems like science fiction for the foreseeable future. But let's flip the script. Could life exist on Jupiter itself? Not the moons, but the planet. Carl Sagan had ideas about this.
Ah, yes, Sagan's floating giants. This is purely theoretical, of course, but utterly captivating. He and E. Salpeter speculated about life forms that could potentially exist in Jupiter's atmosphere, in layers where the temperature and pressure might be somewhat hospitable, at least for exotic life. He drew an analogy with life in Earth's oceans, different types of organisms living at different depths.
So, like an ecosystem in the clouds, what kinds of life did he imagine?
He proposed three main types. First, floaters. These would be enormous, like living balloons, maybe kilometers across, filled with hydrogen or other light gases to maintain buoyancy. They'd be the primary producers, like plankton, maybe photosynthetic, drifting in the upper sunlit layers of the atmosphere. Gigantic, passively floating life.
Kilometer-wide floaters.
Yeah.
Wow. Okay, what else? Hunters.
Exactly. Then you'd have hunters, which would be more mobile predators, also potentially huge, actively swimming or jetting through the atmosphere to feed on the floaters or other life forms. Sagan had this intriguing, slightly chilling thought that for hunters in that environment, the distinction between hunting and mating is not sharp. Makes you wonder what that would look like.
Yikes. Okay, floaters, hunters, and scavengers.
Right. Deeper down, in the darker, warmer layers, he imagined sinkers or scavengers. These wouldn't be photosynthetic. They'd feed on the organic rain falling from above, dead floaters, hunters, or other organic debris, much like deep-sea creatures on Earth depend on marine snow.
But wouldn't they all eventually just fall too deep into the really hot, crushing parts of Jupiter?
That's the key challenge for any atmospheric life there. They'd have to live out their entire life cycle, reproduce, before sinking or being carried by downdrafts into the pyrolytic depth layers so hot and dense that complex organic molecules break down. It's a constant battle against falling into the furnace below.
How did Sagan imagine they might reproduce?
He suggested maybe through dispersals, essentially. The large organisms might break apart into many small, buoyant seeds or spores that could be scattered by winds, allowing the next generation to start fresh in the upper layers, maximizing their chances of survival. It's incredibly speculative, but a fascinating exercise in imagining truly alien life.
It really is. What an amazing journey this has been. We started with ancient Babylonians doing geometry to track Jupiter's path.
Moved through Roman mythology, Jupiter the Sky Father, whose name still marks our week.
Uncovered its faint rings, steered into the great red spot, that centuries-old storm that's still changing.
Learned how it heats itself from within through slow contraction.
Then explored those incredible moons, fiery Io, and especially Europa, with that massive hidden ocean and those tantalizing plumes.
We looked at the amazing Robotic Explorers like Voyager and Juno that have been our eyes out there, and the upcoming Europa Clipper hoping to assess habitability.
And faced the harsh reality of human travel. The immense distances, the supply nightmares, and that absolutely lethal radiation.
Before finally contemplating Sagan's vision of giant floaters in Jupiter's own clouds. It covers such a huge sweep of history and science.
It really does. And maybe that's the final thought to leave you with. While life on Jupiter seems like a long shot, the exploration of its system, especially Europa, keeps pushing us to ask, what does habitable even mean?
Exactly. It forces us to consider life beyond Earth-like conditions, maybe in subsurface oceans, maybe in ways we haven't even conceived of yet. The Jupiter system is this incredible laboratory for challenging our assumptions about where life could be.
It shows how much we've learned, but also how much more mystery there is out there. Every answer seems to lead to more questions. What's the one thing you take away from this deep dive?
For me, it's that sense of dynamism. Nothing out there is static. Jupiter storms evolve, its moons might have active geology, even our understanding is constantly shifting with each new mission, each new discovery. It's a reminder that the universe is this incredibly active, changing place, and we're just beginning to grasp its complexity.
A truly dynamic corner of the cosmos. There's definitely still so much more to explore.